Hope you guys are doing well. Let me just start off by just highlighting a couple of things that I feel like is important. And I'm also recording this video, so hopefully students who aren't here, you'll be able to get a chance to also watch the video and just be reminded of these things. First up, AP exam demo. So hopefully you guys have at least gone through this once or twice to feel comfortable enough where you feel like you're efficient with when you have 5 minutes remaining, are able to take the pictures, upload it, and get it into into the system within the allotted time. So we want to make sure that we're really comfortable with those. So the link is here on my digital learning page. Again, start preparing how you want what you want your resources to be. So I have some highlighted resources that you may want to have on exam day on Tuesday, and also encourage you guys to go through the highlighter and highlight the items that you feel like are important. And also, I think good thing to print out FRQs, weeks 4 through 6, those are good, and as well as the ones that we're going to go over today and tomorrow and Monday. Those are all kind of good FRQs to kind of have you, to kind of help you see hopefully what type of problems we may experience this year in this year's AP exam. Let's see. All right, so, oh, right, so what I wanted to say was, yeah, so your extra credits, some of these are your extra credit assignments. So your extra credits are all due on Monday. Okay, so, because I want you guys to be able to have all these in by Monday, because the point of it is just to get you guys to practice for the problems before the AP exam. So all the extra credit are due on Monday. So Monday night, anytime then is fine. And then what else? Is there anything else? Oh yeah, so you should be getting your e-ticket tomorrow. So sometime tomorrow you should be getting your e-ticket. But even if you don't get your e-ticket, you should be able to log into your My AP account and be able to find that ticket, and that is how you're going to be getting into your exam experience on Tuesday. Again, you're logging in Tuesday at 1:30 so that you can prepare yourself and have everything set up and ready, security questions and all that for the 2 p.m. start time. Let's see, I have up here a checklist here. Make sure that you should be able to see your ID already, but tomorrow see if you can start getting your paper ready. 10 sheets to be safe, numbered 1 through 5 for each of the problems, AP ID and initials. Your devices are charged, and start organizing your resources that you want to use. So Tuesday you'll be taking the exam. I'll be entering and finalizing your grades in Infinite Campus. So senior grades are due on Friday, so I should be able to have all that in before Friday, sometime between Tuesday and Wednesday. And they're going to release the AP exam problems 48 hours, 48 hours, 2 days after you take it. So I'll once it's released, I'll work it out and I'll put it here, in case you want to look at, to try to just do a draft grade, so you can kind of have an idea how you did on the exam. You can kind of grade yourself after the exam, but I'll just post it here on this page. Okay. So again, let me put in chat here. If you have any questions, feel free to type in your question, or you can feel free to unmute yourself as well. All right, so I'll keep track of the chat, see if there's any questions along the way as we go through. So, all right, now hopefully some of you guys have gone through. Okay, so here's a question here. Do you recommend that we use paper for exam or type the answers? I definitely feel like you should take a picture because if you type, I just feel like the notations is just going to be messy. Yes, there's a way to do it, but I think it's a lot more efficient to write all your answers out and then type and take a picture. If you type, I feel like there's, you know, when time is so restrictive, I just feel like it's best to write your answers out, take a picture, and upload it. Okay, so hopefully that answers your question. All right, hopefully you guys had a chance, some of you had a chance to go through these problems, but even if not, that's okay, because I'll work through most of them piece by piece. Now, because of time, I may just go ahead and just go through the solutions, but I think for some parts, I do want to go through piece by piece. Okay, so this is number one. Let me read the problem here. It says, let f be a twice differentiable function. The tables gives the value of f and its derivative. F prime has selected values. We have g of x defined. We have h of x defined. We have a table of values for f of x. We have a table. We have table values for j of x. Okay, let me pause and look at the question here. So Colin, you asked, is it possible to take the exam on 2 different devices? I want to use my PC to look at the problem because it's a bigger screen. Yeah, so that's what I would do. I feel like that's the way that that I would recommend, where you take the exam, you pull the e-ticket on your PC, on your laptop, and then you work the problem out. Have a nice big screen using your laptop. And then the timer is there as well. And then once you work it out, then you take a picture on using your phone, take a picture, and hopefully you have Google Drive loaded, the app on your phone. And then you can use Google Drive to quickly access it on your laptop, and then from your laptop, download it from Google Drive to your C drive, and then you can upload from your laptop. So I think for other courses, using 2 devices is probably not recommended, but I think for calculus, because of the fact that most everyone are going to be taking pictures, I think that is the best way. It feels a little cumbersome, but I just feel like, you know, having, taking everything on the tablet or the phone, it feels like it's a little too much in one place. So yes, I feel like, Colin, that that is the best method to use. But whatever you guys decide to do, maybe you have a way that you feel is more efficient, which is fine. But the important thing is you got to go through the AP exam demo, and you have to decide for yourself what is the most efficient way for you. And I think it'll be, you know, you're running the risk of a disaster if the first time you go through is, you know, if you don't even go through it and the first time seeing it is on that AP exam day. I think that is not recommended. Okay, so part A says, is there a value of C between 1 and 5 such that f double prime of C is equal to -3/4? Let me see if I can move this down a little bit more. Maybe it's hard to see the screen here. Okay. Now, we have information about f prime, and it's asking to see, is there a specific value for f double prime? So with that connection, hopefully we can see this and recognize this as a mean value theorem application, all right? And the idea is, well, I have ordered pairs for f prime, and I'm trying to guarantee an f double prime. If I can locate the slope between the endpoints for f prime, then if that slope agrees with this value, then we can guarantee that f double prime of c exists. So let me go through the steps here. What we're going to do is we know this is an application of mean value theorem, where if I take the slope between the endpoints, and if that slope between the endpoints exists, then we can guarantee for f prime. Now that's what mean value theorem gives us, but if we adapt it, we can adapt it for 1 degree lower and say f double prime is equal to f prime of b minus f prime of a over b minus a. So this is the formula we're going to use, right? We want to see, can we guarantee can we figure this out to be negative 3/4? Because if this is negative 3/4, then we can make that claim, okay? So our endpoints are provided for us. So that's our a value, that's our b value. We're going to plug it into this f prime formula here. So f prime of 5 minus f prime of 1 over 5 minus 1. And this is perfect because we have ordered pairs from our table. So f prime of 5 is negative 2. F prime of 1 is just 1. All over b minus a. So this ends up being negative 3/4. And this matches perfectly with what we're trying to prove. So we can say by mean value theorem, since our function is continuous on the closed interval, differentiable on the open, then there must be a point c where f double prime of c is equal to negative 3/4. Right? The slope between the endpoints of this graph is negative 3/4, so there must be a slope of the tangent line that matches that value. Okay. All right, number 2, part B. I think I may want to work this out part by part, or work through all the pieces here. All right, so part B says, let k be the function defined by k of x equals f of j of x. Write an equation for the line tangent to the graph at x equals 2. Okay, so in order for us to find our tangent line, we need order pair and we need slope. All right, so let's find our order pair first. Here's our formula. Oops. So if I want to find order pair, I need to plug 2 in. So we can say k of 2 is equal to f of j of 2. So now we have to kind of piece this together to find this order pair. So piece by piece here, j of 2. Okay, so we look at the graph here. So j of 2 is right here. That's negative 1. So we got this inner portion found. So now we can look at this full thing here, f of negative 1. So f of negative 1, we go back to our f graph here. F of negative 1 is equal to 4. So k of 2 is equal to 4. Okay, so that's our order pair. 2, 4. The next part is we have to find the derivative, or we have to find the derivative so we can then find the slope. Okay. All right, so if I start off with k of x, and I need to find the derivative, we need to recognize this as chain rule. Notice that there's an outside function with the f, there's an inside function with the j, and we have to make sure that we take turns with each portion so that we can fully apply the derivative. So chain rule here. So before we can plug 2 in, we have to first find the derivative. So outside's derivative is f prime of j of x multiplied by the inside function's derivative. So j of x becomes j prime. So now we can start putting information in, right? Our x value that we're trying to find the slope is at 2. All right, so let's see if we can just like how with this function, we want to kind of piece together, and so we can get it down to a numeric value here. So j of 2, we look for j of 2, again, right at -1. So we'll replace this with -1. But everything else is still there, right? All right, so now this is a little bit easier to interpret now, right? F prime of -1, so F prime of -1, we go to our F graph here. We have F prime order pairs here, so F prime of -1 is -3. So this part becomes -3. And then J prime of 2, this is asking for the slope of the J graph at 2. So it's not asking for the order pair, it's asking for the slope. And if we want to find the slope of this line segment, just pick any 2 points and then just do the slope, right? So the slope of this line, we go down 2 over 1, so -2 over 1. The slope of this line is -2. So that goes over here. So k prime of 2 is -3 times -2. -3 times -2 is equal to 6. So k prime of 2 is equal to 6. All right, so we have the information that we need. We have our order pair. We have our slope. And now we're ready to put in the point slope form. Okay, so we've fulfilled what the problem is asking for, write an equation for the line tangent. Okay, there's part B. All right, part C. It says find the slope of the tangent line to the graph of g at x equals pi. So we want to be able to find the slope of the tangent line. So we need to find the derivative of g of x. And then we have to, after we find the derivative, we'll plug in and evaluate the derivative at x equals pi. So as a couple of reminders, the derivative for sine of u is equal to cosine of u times u prime. The derivative for e to the u is e to the u times u prime. Okay. And yeah. Let me work it out on a separate sheet here. Okay, so the graph of g or sorry, the function of g. We need to find the derivative. So I think this is where make sure that you are, that you have your derivative integral rules printed out in front of you. So if you need any derivative rules, you can quickly access it. Right? You want to make sure that you have it handy and ready, so you're not having to search for it on that online when you're taking the exam. Okay, so we have to go through chain rule here. So g prime. Sine of u becomes cosine of u times u prime. And this, there's 3 functions here. There's e to the u, there's cosine of u, and there's also this 2x. So we have to go through those 3 pieces here. So hopefully we see that there's the outermost portion, which is the e to the u. There's the inside portion, which is this cosine of parentheses, and then there's the innermost function, and that's the 2x. Okay, so there's a lot going on here that we have to find the derivative. We got to involve all 3 pieces here. So the derivative for e to the u is just e to the u. So the exponent doesn't change. Now we're ready for the inside function, cosine of parentheses. So the derivative for cosine of u is negative sine of u. And then finally, the innermost function is that 2x. And that 2x we do times 2. Okay. So once we have our derivative, then we can just plug in pi in for all the x's. Okay, so in the interest of time, I'm just going to kind of go through the answers here. So the importance, the step I wanted to show you was making sure that we can that we know where the derivative is coming from and all the pieces that goes into it, all the steps that goes into it. But as soon as we find the derivative, we're just going to replace every x with pi and then see if we can get this down to a numeric value here. So cosine of 3 pi, that's the same thing as cosine of pi, which is -1. -1 times 3 is -3. Cosine of 2 pi, that's going to be 1. So e to the first power is just e. It's just e. Sine of 2 pi is 0. So anything times 0 is 0. So this whole expression is just going to turn into 0. So -3 minus 0. So that's -3. Okay. All right. Any questions there? All right. Let's look at part D. Part D says find h of 4 and find h prime of 4. So we have to, so to find h of 4, we have to just use the definite integral. Oh, sorry. Yeah, h of 4, we use a definite integral here, this formula. Integral from 6 to 4 of j of x dx. Now, we have to read the graph, right? I'm sorry, h of x. If we want to find the definite integral of j of x, we know we have to involve area under this graph here. But we want to read the graph from left to right. So we see that this is out of order. I'm going to rewrite this as negative integral from 4 to 6. And now I'm going to go through and see if I can find the regions that we need, right? We need to find that region from 4 to 6. So 4 to 6, that's going to be this region here. And that's above the x-axis, so that's just 1/2 base times height. And that's equal to 3. So we know that the definite integral from 4 to 6, that's just going to be equivalent to 3. There's a negative that hangs out in front, so we keep that negative. Find h prime of 4. Now to find h prime of 4, let's first find h prime of x, right? So to find h prime of x, we have to find the derivative of this expression. So you don't have to go through all this step, but I just want to show you that this is what happens when we combine two operations that are going to cancel each other out. So derivative integrals, they're going to kind of cancel each other out. Okay, we plug the upper bound into the function, and then that's going to be our h prime. So h prime is simply j of x. Okay. So now we can find h prime of 4. So h prime of 4 is just corresponds to j of 4. And j of 4 is just the order pair on my j graph. So j of 4 is just going to be 0. So we found h prime of 4, which is j of 4, which is 0. And we also found h of 4, which is the area between on the graph of j from 4 to 6. Okay. For part E, I think I'm just going to show the answer here. So for part E, on what interval is the graph increasing and concave down? So what we're going to do is we have to recognize that this basically is the H prime graph, right? We've established that the J is the H prime graph. So we can go ahead and mark our derivative graph. We can also call this the H prime graph. Okay, and then we know anything above is positive slope, anything below is negative slope for H, anything on the x-axis is slope 0. So we can go ahead and create our slope sine line. So from 0 to 1.5, positive slope, there's a slope 0 at 1.5, slope 0 at 4, negative slope from 1.5 to 4, and then positive slope all above the x-axis from 4 to 6. And then we can also create a concavity sine line because we also need to grab information about concavity. So we can pick out the peaks and valleys, right? Peaks and valleys are going to indicate where your POIs are. So we have POIs at 1, POI at 3, point of inflection at 5. And then the positive and negative slope will correspond to concave up and concave down. So after all that, this is what we can gather. Creates a slope and concavity sine line. And once you have that in place, then we can kind of read the graph and decide, all right, we can line everything up, right? Line everything up between your slope sine line information and your concavity sine line information. And then we want to look for a place where my H graph is increasing and concave down. So I want positive slope and concave down. So positive slope and concave down. I see that between 1 and 1.5, right? Between 1 and 1.5, we see that is an interval where we see both properties existing, right? Positive slope and concave down. And then another interval is from 5 to 6 because we see positive slope and concave down, right? So if you line everything up, it's a little bit easier to make your conclusion. All right, any questions there with E? Okay. Part F, find the absolute minimum, absolute max on the closed interval. So whenever you see absolute min, absolute max, that should be on the closed interval. That should be a hint that the problem is trying to get you to reference extreme value theorem, right? So let's think about extreme value theorem. Extreme value theorem is where we gather information about from the endpoints, and we also gather information about the relative min and relative max. Okay, so we're going to find H of 0, H of 1.5, H of 4, and H of 6. And after we find all those values, then we can compare them and see which one is the highest y value, which one is the lowest y value. Okay. Okay, I'm going to, just in the interest of time, I'm just going to kind of go through the steps here. So we identified that we want to test endpoints and critical points. So we want to find H of 0, H of 1.5, H of 4, and H of 6. And the formula that we're going to be using is built directly off of this. Right? We have a definition explicitly defined for H of X, so we'll use it. Okay. All right, it's defined from 6 to X, so we always have to fit where that X is, and then once we have that, then we can decide, all right, if something's out of place, we can manage it. All right, so we see the 0 is out of place. We want that lower bound to be the smaller value, so I'm going to flip the bounds, change the sign. I'm going to total the area from 0 to 6 on my J graph. So 0 to 6. I did the work already beforehand where I did, these are all triangles, so 1/2 base times height for each of these triangles, positive, negative, positive. And if I total from 0 to 6, I'll do 0.75 minus 3.75 plus 3. Okay. Now that's going to give me 0, so negative 0 is still going to be 0. Okay. I also want to do that for 1.5. So h of 1.5 from 6 to 1.5 again is out of order. I'm going to flip the signs. So 1.5 to 6. So that's going to be from here to here. So that's negative 3.75 plus 3, which gives me negative 0.75. But because I flipped the bounds, there's a negative in front. That's going to change the sign. So positive 0.75. Okay. H of 4 is from 6 to 4. The bounds are out of order. So I'm going to flip the signs, pull the negative out in front. And then from 4 to 6, that area is just 3. And because I flipped the signs, there's a negative hanging out in front, so negative 3. Okay. And finally, h of 6 is the definite integral from 6 to 6, j of x dx equal to 0. Okay, Colin had a question here. When testing critical points for extreme value theorem, do we need to test concavity points? Okay, so we don't need to do that because we only apply extreme value theorem for relative min, relative max, and endpoints because there's no chance that points of inflection can ever be the highest and lowest points on the graph. So let me kind of show you an example of that. Let's say we have endpoints here. Let me make this smooth here. All right, so we only test endpoints and critical points because even though there are points of inflection that may occur on the original graph, concave down to concave up, there's no chance a point of inflection can be an absolute max or absolute min. So we never have to worry about these points of inflection. Even though on the F prime graph, they kind of stick out. You feel like, okay, maybe these are potential max and mins, but you're looking at the F prime graph. So any peaks and valleys are going to turn out to be just these transition points from one concavity to the other. There's no chance that these can ever be absolute max or absolute min. So when you do extreme value theorem, you only want to test your relative min and relative max, okay, off your slope sine line. We don't care about the critical points from the second derivative. Okay. Now, sometimes they may overlap. If they overlap, then we just care about these points. Okay, so we don't care about these for EVT. Okay. All right, so if we compare all these points, one of these must be the absolute max, one of these must be the absolute min. So the highest y value that we see is 0.75 at 1.5, and the lowest y value is -3 at x equals 4. So there's our answer. Okay. All right, part G. Okay, this is last part for number 1 here. Evaluate the second derivative, f double prime of 2x from 1 to 3. Put a star next to this. I feel like these are problems that I feel like test makers will like to put on the exam because this is a way that they can test to see if a student really understands U substitution without the advantage of using calculator. This is going to be something that you can't use your calculator for. And so when they stick something in function notation, it forces students to have to work it out by hand. And also, when we work it out by hand, the College Board can know, how well a student understands a concept like this. Right? We can't just plug this in the calculator. So I really like this problem in terms of a potential one or some variation of this showing up on the AP exam. So we don't have f double prime, right? We have nothing involving f double prime. So let's see if we can get this into an f prime form. So we're going to go through antiderivative. So let me remind us on first theorem of calculus here. So first theorem of calculus says the definite integral from a to b of f prime of x is equal to, well, dx is equal to f of b minus f of a. So the antiderivative is going to force this expression to move up a level, right? So f prime will turn to f, right? So I'm going to adapt this into something that we're going to be seeing for this particular problem. And that is where we're starting at f double prime. And I'm going to match it where I don't have to go through u substitution there. So let me rewrite it in this form. F double prime of u, if I can get it into this form, then that's the same thing as making this go up a level from f double prime to f prime. And once it turns into f prime, I can then plug in my upper and lower bound. So here's first theorem. This is the one that we're going to be using. This is the one that we're going to adapt to for this particular problem that we're using. Okay, so we're going to try to work our way to this form, and then we can use that. Okay. So that 2x is sticking out. We got to deal with that 2x. So the way we deal with it is we're going to go through u substitution. And the reason why is because that coefficient inside is going to cause something to occur outside. So if we don't keep track of that 2x, then we're missing out on the full solution. So go through u substitution here. Right, we're trying to get this to look like this, so we're going to go through u substitution. All right, derivative du dx equals 2. Solve for dx, we get du over 2. Okay. I underlined the portion that we want to substitute. Replace 2x with 2. Sorry, replace 2x with u, replace dx with du over 2. All right, so hopefully we see that this is going to produce a 1/2, and that 1/2 is going to stick with, it's going to stay with the problem until the answer here. All right, so now we have something in the form we can now apply, right? F double prime is going to turn to f prime. The 1/2 is going to stay. And now we have to work in the bounds. Careful here. You see how there's a 1 and 3 here? We don't want to use the 1 and 3 at this point because you see how the 1 and 3 is not in terms of u. So there's a mismatch right now. If we use the 1 and 3, then we're not fully making a match that we need. So we have the antiderivative, but let's bring this back in terms of x, right? We went through u substitution. We kept track of 1/2, and now let's bring it all back. Let's bring this back in terms of x. Okay. Now we have a matching variable. Now we can work in the bounds. Okay. All right, so now we're ready for our upper bound. Plug 3 in for x. F prime of 2 times 3, that's f prime of 6. And then f prime of 2 times 1, so that's 1/2 f prime of 2. So let's see, can we make any more progress here? F prime of 6, we see is positive 2. And then f prime of 2 is 3. Okay. So we have 1/2 times 2 minus 1/2 times 3. So that's 2 over 2 minus 3 over 2. So that's negative 1 over 2. All right. Yeah, so this is a way that College Board can get students to show whether they fully understand u substitution, but it's not a problem that they can stick in the calculator. Okay. All right, so any questions with that for number 1, part A? For number 1, mock exam 1. Okay, question from Mahi here. It says, will the exam be a 3-part and then a 2-part FRQ? So it'll only be 2 questions, okay? I printed out multiple pages for number 1, just so I can have a lot of room to work. But you're going to get 1 problem that's going to be an extended FRQ. You're going to be given 25 minutes to work. So I just added a couple more sections to make it feel like 25 minutes. And then number 2 is going to be a little bit shorter, and you're going to be given 15 minutes. So you're getting two FRQs. 1 FRQ is 25 minutes. Now, we don't know how many parts there are. I'm just guessing how many parts there are going to be. I feel like it's at least 5 or 6 parts, because normal FRQs with 15 minutes are usually 3 to 4 parts. So I'm guessing 4 to 6, 5 to 6. And then FRQ, that's only 15 minutes, is probably just 4 sections. So I'm guessing it's going to be 6 parts, 5 to 6 parts for number 1, and then 3 to 4 parts for number 2. Okay, so hopefully that answers your question. All right, number 2 here. Let's see. All right, number 2 says find the second derivative at the point 1, 2. So this is the notation for finding the second derivative. So that means we have to find the use the first derivative and move to the second derivative. Okay, so dy dx is equal to 1 over x times y. And it's really the same thing as xy to the negative 1. I'm going to do that here. Okay. So if I want to find the second derivative, I have to recognize this as an outside and inside portion. I have to go through chain rule and then product rule. So there's an outside portion, which is the parentheses to the negative 1. We got to do the derivative for that. And the inside portion is the xy, which we're going to have to rely on product and implicit here, okay, to find the derivative. Okay, so outside derivative first. The derivative for parentheses to the negative 1 is negative 1 parentheses to the negative 2, with the xy still intact, multiplied by the inside function's derivative. So x times y, to find the full derivative of x times y, we have to go through a product rule within that portion, right? So we got to do f prime g plus f g prime. So here's my f, there's my g. So f prime, x becomes 1. G function is the original. Back to f. And then g prime, y's derivative is just 1 dy dx. Okay. It says find the second derivative at the point 1, 2. So we're going to start putting all the plugging 1 and 2 in for all the x's and y's. So to indicate that, I'm going to plug in my order pair. Sorry, there's a plus here. Now the dy dx, we have to find a value for that. So dy dx, that means we need to figure out what dy dx is at 1, 2. And if I plug 1 and 2 in for dy dx, I'm going to get 1 over 2, which is 1/2. So I can replace dy dx with 1/2. Now that's a messy answer here, but technically they should accept this answer. This is an unsimplified, but unsimplified is perfectly fine. Okay, so you can leave your answer unsimplified as long as it's equivalent to the reduced answer. Then there's no issue. Okay, So if you were to reduce this, it would go all the way down to -5/8. But I think this is fine. We can stop here. Okay. Also, in the interest of time, if you have the correct answer, if they're going to accept it, then move on, right? If you continue working, you're introducing the possibility of making a mistake. And if you make a mistake here, then you'll lose points here. And also, you're losing time. You're losing precious time for problems that you could be working on elsewhere. Okay, part B. Write an equation for the line tangent to the graph at 1, 2, and use it to approximate. Okay. So let me just show the work for this in the interest of time here. So if we want to find the equation of a tangent line, we need order pair, which is given to us, and we need to find the slope, which we can just plug 1, 2 into the derivative, and that gives us 1/2, right? 1/1 times 2, which is 1/2. So let's do one thing at a time first. Let's find that tangent line equation. So we have our order pair, 1, 2. We found the slope by plugging 1, 2 into the derivative, which is 1/2. So once you have your order pair and your slope, you put in the point slope form. So y minus 2 is equal to 1/2 times x minus 1. And we have our equation. Okay. Now that's the first part, right? You have your equation. You got y by itself. You got your tangent line equation. So now we're going to use this to approximate f of 1.1. So you're going to take your equation and you're going to dump that decimal value into the x. So when we do that, we get 1.1 minus 1. You can use your calculator here, and this will get you down to 2.05. Okay. So linear approximation, don't overcomplicate this. You're just finding a tangent line equation, which you know how to do. We've been doing that since September. And then you just do one more step. You're just plugging that decimal into that tangent line equation, and there's your linear approximation. Okay. There's a second part here, though. It says, is the approximation for this point, because this is an approximation, right? And what the problem is asking about is this going to be higher or lower than the actual value, right? We know this is an approximation. This is not the exact value, but is this going to be, it's going to over approximate or it's going to under approximate? Okay. So it says, explain your reasoning. Now this, we don't have the graph in front of us to see whether it's going to over approximate or under approximate. So this is an instance where we have to rely on the second derivative test. So this is what the second derivative test does for us. We know the second derivative value at 1, 2. If we were to reduce that previous part that we found, right? Yeah, the previous part that we found, which you can leave it in this form, but I guess in this case, maybe you can see that it's obviously going to be a negative value. So it's a negative second derivative. So we need to be able to visualize negative second derivative as concave down. Okay, so that's important, right? We need to visualize the fact that it's concave down because that's important. Now, if a graph is concave down, right, which looks like this, then any line that you draw, right, any tangent line that you draw is going to end up being above the graph. You see how this tangent line is above the graph. So any approximation on this tangent line is going to sit above the curve, and that is how we're going to make our conclusion. The fact that the graph is concave down, the tangent line has to sit above the curve, and therefore our approximation is going to be an over approximation. This line is going to give us a higher value than the actual point on the curve. Okay, so this is an application of second derivative test. Okay, part C. Now let me put it on this page here. All right, part C, find the solution for the given differential equation. So that means it's asking for us to solve the differential equation. And that means we have to go through our steps, cross multiply, and be able to find our antiderivative. So I'm going to cross multiply here. And then we're going to separate our variables. So we have dy over dx is equal to 1 over xy. Okay, we're going to cross multiply here. And we get xy times dy is equal to 1 dx. But once we cross multiply, we see that, all right, there's no more denominator. However, we don't have full separation yet, right? We want the y's on the left, but we want the x's on the right. So this x is out of place. We're going to divide the x over. Okay. Take the antiderivative. And now we're ready to find our, go through our steps. We know this is just going to be a nice power rule here. This, we have a special rule, right? The integral of 1 over u du is natural log of u, so plus c. So as soon as c shows up, we can go ahead and find that c value. So we're going to plug in, find the c value using order pair 1, 2. Okay, so 2 goes in for y, 1 goes in for x. Natural log of 1 is just 0, so we get 2 is equal to 0 plus c. So c is equal to 2. Okay. So now that we have our c value, we're going to dump this back in where we initially started making our substitution. So now what we have here is we have y squared over 2 is equal to natural log absolute value of x plus 2. And now we just want to solve for y. So we want to algebraically start to get that y by itself. So if I multiply everything through by 2, move everything over to the right side, or just that fraction to the right side, we get 2 natural log absolute value of x plus 2 times 2, which is 4. And now we have to get y by itself, so we're going to take the square root of both sides. But we need to recognize this as two separate solutions, right? This is a positive square root. And there's also a negative square root. But both of these are not going to be included. We only get to choose one. And the way that you choose between a positive and negative square roots, you're going to use this order pair. Okay, you're going to use the order pair that you use to find c to determine which solution. And the key thing is to pay attention to this y value, right? Whatever the sign of the y value is the sign that you want between the positive and negative square root. So we see that's a positive 2, so that's going to guide us to the fact that it must be the positive square root. Okay, so look at the y value, and the y value is gonna help guide you to your answer, or the sign of the y value. All right. Okay, part D. Let g be a differentiable function such that g is equal to the inverse of f. So what is the value of g prime of 2? So this is a concept that we went through in first semester when we went through chapter 5. So let me highlight and help you recall what we do for that. So here's the big idea. Big idea is that a function and its inverse will have slopes that are opposites of each other, reciprocals of each other at their corresponding points. Okay, function and its inverse. So for instance, first off, a function and its inverse, they're going to have corresponding points in the sense that if I have order pair f that's 1, 2, then my g function, if it's a true inverse, it's going to be order pair of 2, 1. Okay, and if I can figure out the slope of my f graph, in this case, we're going to find that as 1/2. then the slope of my G graph at its corresponding point, right? Not at 1, but at its corresponding point is going to be the flipped version of that value. Okay. So for part D, it says let G be the differential for function that where G of X is the inverse of F. And we know we can find the derivative for F, right? The derivative for F, we're sitting right here. 1 over 1 times 2, which will be 1/2. So we know the slope of the F graph is 1/2. So we know this statement is true just based off of part A. Now, if this is true, then G prime of 2, right? Not the same point, but at its corresponding point. Okay, and we know it's a corresponding point because that is we know if the order pair is 1, 2 for my F function, then my G function must be 2, 1, right? So whatever the slope is for my F graph, I can just flip it, and that must be the G graph. Okay, so our G prime of 2 is equal to 2. Okay. Sometimes I think I also use this table to kind of help move us along here. If I fill in all my information for F and G, my order pair for G is 2, 1. My order pair of F is 1, 2. F prime of 1 we found using the differential equation is 1/2, which means that G prime of 2 must be the flip version, which must be equal to 2. Okay. Okay, this problem took longer than I expected, but I think it makes sense since we worked through every part piece by piece. So I think what I'm going to do is I'm going to maybe just quickly go over number 2. So hopefully I can get through this in the next 15 or 20 minutes. I don't want to hold you guys too long if you want, but I also understand that maybe you want to see this problem. So feel free to ask questions for number 2 or if I'm going a little too fast, you want me to kind of slow down. Okay, so for number 2, here's the idea that we have, this is a particle motion problem. And number 1 says, find the average acceleration for the particle. Okay, so average acceleration, we have to understand how to define average acceleration. Okay, so average acceleration is defined as the change in velocity over the change in time. Okay, change in velocity over change in time. So we just take the endpoints that's provided for us, and then we just do v of 10 minus v of 0 over 10 minus 0, and we get 2 over 10, which is 1/5. Part B, explain the meaning of the definite integral of absolute value of v of t. So absolute value of v of t, we have to understand this is a notation for total distance. Okay, and we're going to approximate the total distance by using trapezoid approximation. So make sure you have this formula ready. So in case it's asking for a trapezoid rule or trapezoid approximation, you have that formula ready to go. And so we do width over 2, height 1 plus height 2. Okay. So we're pulling this off of the velocity information here. And we just want to find the width in each of these intervals here. So from 0 to 2, that's 2. That's an interval of 4. That's a width of 4 from 6 to 10. But the slight adjustment there that we have to make, okay, and then when we do height, we choose the heights at the endpoint. So we choose 2 and 0 for the first one, 0 and -1 for the second, and -1 and 4. But a further adjustment is the fact that we're doing total distance. So any height we're gonna treat as a positive value. So that's why these have been changed to positive ones. Okay, and then we total those up, and that'll give us our distance traveled by particle Q. For part C, evaluate the definite integral from 0 to 10 of a of t. So we can get this in terms of velocity, but we can push this through first theorem. So we know acceleration, if we push it through integral, it's going to go up a level from acceleration to velocity, and then we plug in our velocity, v of 10 minus v of 0, and that's just 4 minus 2. Look at we can look at our table to find that. Okay. For number 2 here, determine whether a particle is speeding up or slowing down. So if we want to determine speeding up and slowing down, we have to compare signs between velocity and acceleration. Okay. Okay, so for Q, there's our velocity, there's our acceleration at 1. So we have 3 and -2. And so we see there's opposite signs. So therefore, our particle Q must be slowing down since we have different signs. Now for particle P is based off of this piecewise function. So we need to, this is our velocity function. We can find the derivative to create the acceleration information. And then we can plug 1 in for our velocity and our acceleration. So it's going to be the first piecewise for both of them. And when we plug 1 in, we're going to get 4 for this, and we're going to get 0 for the second one. And we're not going to get a full way of determining because these are not same signs or opposite signs. So it doesn't apply for the second one. Okay, we need these to be either both positive or both negative, or one positive and the other negative, and 0 doesn't fall into that category. So particle P is neither speeding up nor slowing down. Okay. For part E, it says find the limit as t approaches 3 for our expression here. So if we want to find a limit for the first thing we do is we plug in that 3. Okay. Plug in the 3 in for the t values. And when we do that, we're going to get 0 in the numerator, and we're going to get 0 in the denominator. And if we get 0 in the numerator and 0 in the denominator, that means we can apply L'Hopital's rule. Now, I do want to point something out here. Recently, I attended a webinar, and one of the AP leaders for one of the graders did not like this notation. So I think the safer way to go about doing this, knowing that it's L'Hopital's rule, is you want to separate this out. So you want to limit as t approaches 3 for the numerator, and then do it for the denominator separately. Okay, so what I mean is you write it out this way. So rather than putting everything under with numerator and denominator, you write it out separately, and you don't show that 0 over 0. Okay, I think this could be a potential issue where they don't like seeing that 0 over 0. They just want to see that you found the limit for the numerator, you found limit for the denominator, and then from here just say, okay, I have the information that I need. Now I'm going to go through L'Hopital's rule. So now, once you have that, don't do 0 over 0. Just show this work, and then jump directly to find the derivative of the numerator and denominator. So e to the u becomes e to the u times u prime. Negative t becomes -1. 2p of t becomes 2p prime of t. Plug 3 in, and then we get our expression, our numeric value, which is -1/8, and that is our answer using L'Hopital's rule. Okay. All right, for F, h of t is q over 3 minus t squared. Find h prime of 1. To find the derivative, notice that this is set up as a numerator and denominator, so we have to go through quotient rule. So pretty straightforward, right? Go through quotient rule, f prime g minus f g prime all over g squared. Once you have your derivative expressed, then replace every t with 1. And then once you have this, then you use your table of values to fill in. Q prime of 1 is just 2. Sorry, Q prime of 1 is just 3. And then Q of 1 is just 7. And then once you're down to numeric value, get it down to equal to 5. For G, do particles Q and P both change directions in the interval from 0 to 4? So if we want to figure out whether particles change direction, we're going to have to set the velocity equal to 0 first. So we set the velocity equal to 0, factor, solve, and we get -1 and 3. But -1 is outside the interval, so just 3. And then we test the signs, and we see that, okay, It's moving to the right, stops, and continues moving to the right, so there's no change in sign. If there's no change in sign, then there's no change in direction. For particle Q, we have to rely on the table of values. So particle Q, we look at the velocity. We see that it changes from positive to negative, and then from negative to positive. So there's going to be, I'm sorry, this is going from 0 to 4. Okay, so from 0 to 4, there's at least 1, right? Because it goes from positive to negative. So in this instance, it has to change direction at least once. Okay, and so we can say by IVT, because we have a positive on one end and negative on the other, it has to cross through our target y value, or our value of 0, our velocity of 0. Okay. All right, last one here. Let me just go through quickly. Number 2. We have our function as e of x minus x. It says find the critical points. So critical points mean just set f prime equal to 0. Once you get f prime equal to 0, you solve for x. E to the x equals 1. Take the natural log of both sides. Get that x to come down. X equals 0. And then you test your interval here. Plug -1 into the derivative, and you get a negative value. You plug 1 into the derivative and get a positive value. So negative followed by a positive, we can guarantee there must be a relative minimum. Okay. For part B, write the equation of the line tangent to the graph. So tangent on equation, we need to find order pair, and we need to find slope. So order pair, we just plug 1 into the original function, e to the 1 minus 1, which is e minus 1. And then to find the slope, we plug 1 into the derivative, which is also e minus 1. So we take our order pair, we take our slope, and then point slope form. Part C, given that the definite integral from 0 to a of f of x is equal to f prime, find f of a. So let's go through this process here, right? We know f of x is e to the x minus x, so I'm going to go through my antiderivative step. E to the x stays at e to the x. X becomes x squared over 2. I do power rule for both terms. Power rule for the second, and e to the u rule for the first. And then I plug in my upper bound minus lower bound. And that gives me e to the a minus a squared over 2 minus e to the 0. Okay, so careful. This 0 is not going to wipe this term out. This e to the 0 is still a leftover term of 1 minus 0. So all this is the result of the left side, is equal to f prime of a. So f prime of a is just taking a and put it into my f prime of x, which is e to the a minus 1. So now I have something that we can set equal to each other. This is the result of the left side. This is the result of the right side. We're just trying to solve this equation here. The e to the a will go away. The -1 will go away. We're left with -1/2 a squared is equal to 0. We solve for a, and we get a is equal to 0. All right, last one here. Suppose that y squared f of x equals y minus 4. Find the derivative. So if I want to find the derivative, notice that these are 2 separate terms. We got to go through product rule. There's also y involved here, so we have to make sure we include implicit differentiation. And there's also y here too, so also implicit on this side. Okay, so product rule, f prime g plus f g prime. So f prime, y squared becomes 2y. We just took y's derivative, so we need to include dy dx. There's my f function. There's my g function. And then f back to y squared stays the same. And then the second function becomes g prime, becomes f prime. So we took care of the derivative of the left side. And now the right side, y becomes 1 dy dx. 4 goes to 0. And now we just want to try to solve for dy dx. So I'm going to group the dy dx on the left side, move all the dy dx terms on the left, move the y squared f prime to the right side. Becomes negative y squared f prime. Factor the dy dx out, divide the parentheses over, and then maybe we can replace the f prime and f with the notations here. Yeah. So I guess we can leave it in this form unless the problem says to express your derivative in terms of x and y. If it does, then we have to replace the f prime with the f prime expression, and then replace the f with the f of x expression. And you can leave your answer on some, any form is fine. You don't have to get it to a specific notation, or a specific with or without parentheses is perfectly fine. All right, so we're able to go through number one in mock test one, exam one in detail, and number two I kind of just went through. But feel free to, if you have any questions, you can ask now, or you can feel free to message me and I can go through in detail. But tomorrow, I'll try to be more aware of the time and try to fit both of the FRQs, 3 and 4, into an hour time frame. Okay, and final, and I put up a couple of more reviews here. So if you have time, or if you're willing, if you want the extra practice, there are some more here. Okay, but these are extra credits. So if you're working through this as I go along, then you can turn those in, and I'll give you points for put in the grade book. Okay. All right, any questions for me? All right, thanks everyone. Hope you guys have a good weekend. And if you are gonna come tomorrow, then I'll see you tomorrow. All right, take care, guys. Thanks for being here.